ever like flipped through one of those Earth through the ages things? You know, those illustrations?
Like the evolution of Earth.
Yeah. And like wondered what it actually looked like billions of years ago.
Yeah.
Well, that's what we're doing today on this deep dive, like hopping in a time machine.
How far back are we going?
We're talking ancient geology.
Okay.
Specifically, a study about the Olondo greenstone belt.
Okay, I've heard of greenstone belts, but refresh my memory. What is that again?
Yeah, so get this. It may like rewrite what we thought we knew about early Earth.
Really?
Yeah.
Wow. Okay. So what's so special about this Olondo greenstone belt?
So the research, what's so cool about it is it's like a window into the Mesoarchean era.
Mesoarchean era. Okay, so we're talking
Over 3 billion years ago.
Wow, that is going way back. So like what was happening on Earth way back then?
We're talking like continents in their infancy.
Oh, wow.
Not the giant land masses we see today.
Gotcha. Okay, so back to this Olondo greenstone belt. I'm picturing like a hidden temple in the jungle here.
Okay, so think more like vast, rugged landscape in Siberia.
Okay, so not a jungle.
Not a jungle.
More like desolate and rocky.
Yeah, it's this huge slab of ancient rock.
Yeah.
And its composition is what makes it really special.
Composition. What kind of music the rocks are into?
More like the ingredients.
Okay.
So you know how like most greenstone belts have a lot of basalt?
Yeah, volcanic rock.
Yeah, they think of it like the standard recipe.
Okay.
The Olondo greenstone belt, it's got these other rarer rocks like dunites, comitatic basalts, and dolitic basalts.
Okay, those are some serious tongue twisters.
I know.
Can we get the layman's explanation on those for those of us who haven't like geeked out on geology textbooks recently?
Yeah, so imagine Earth as this giant layer cake.
Right.
Crust on top,
Yeah.
mantle in the middle, and then like the core is in the center.
Right.
These rocks, dunites in particular, are like finding a chunk of that ancient mantle.
Yeah.
Just like frozen in time.
Oh, wow.
Yeah.
So like instead of digging up Earth's baby pictures, we're digging up its like
Yo.
molten rock and volcanic eruption.
Exactly.
Okay.
But these pictures tell a fascinating story.
Okay.
The fact that we're finding dunites in the Olondo greenstone belt suggests that something incredible happened, like a massive melting event deep within the Earth's mantle.
Okay, so how do we know this wasn't just like a random isolated event? Like, why is this melting event such a big deal for like understanding early Earth?
Great question. So these dunites, they're not just any old rocks. They actually hold clues to something really fundamental. Plate tectonics.
Plate tectonics, as in continents drifting around like giant puzzle pieces?
Exactly.
Yeah.
But here's the thing. The question of when plate tectonics started is a huge debate in geology.
Okay.
Some people think it was gradual. Others think it started much earlier.
Okay.
And the Olondo greenstone belt, it's providing some of the earliest evidence we have for this process happening.
Real?
Yeah, like potentially changing our whole understanding of how Earth's crust evolved.
Wow, okay.
So plate tectonics happening earlier than we thought. That's huge.
Yeah.
But how can we be sure these rocks are actually telling us what we think they are? Like, it's not like we can carbon date something that old, right?
Oh, yeah, you're right. Carbon dating wouldn't really help us with something this old.
Right.
But these researchers were clever. They used not one, but two different dating methods.
Oh, really?
Yeah. Samarium neodymium and uranium osmium dating.
Okay, those sound like elements on the periodic table.
Exactly.
So like way more precise than carbon dating.
Yeah, think of it like getting a second opinion from a specialist.
Gotcha.
Just to be extra sure about the diagnosis.
And what happened? What did those results show?
They confirmed it. These dunites are over 3 billion years old, which makes the Olondo greenstone belt one of the oldest sites where we see evidence of plate tectonics actually happening.
Wow.
And remember those other rock types that we mentioned earlier?
Yeah.
The comatic and tholitic basalts?
Right. Different flavors of volcanic rock.
Yeah.
What makes them so special again?
Yeah, so they add another layer to this whole mystery.
Okay.
Because each type of basalt tells us about the kind of volcanic activity that was happening.
Okay.
So comatic basalts, for instance,
Yeah.
they come from incredibly hot, deep plumes of molten rock, like shooting up from the mantle.
Okay.
Imagine a volcanic eruption so powerful that it makes Mount Vesuvius look like a kid's science project.
Oh, wow. Okay. So like these comatic basalts are giving us this picture of a super fiery early Earth.
Yes.
Okay. So then what about the tholitic basalts? What's their story?
Okay, so phyllic basalts, they form in a totally different way.
Okay.
Think about like what happens at mid-ocean ridges today, where
Yeah.
you have tectonic plates spreading apart
Yeah.
and then magma rises up to fill that gap.
Right.
That's how phyllitic basalts are formed.
So finding both of those in the Olondo greenstone belt,
Yeah.
it's kind of like finding evidence of two totally different volcanic environments just like smashed together in one place.
Exactly. And that's what's so exciting because it points to this young Earth that was incredibly dynamic
Yeah.
with all these multiple forces just like jostling around and shaping the planet's surface. Like
Right.
the Earth was experimenting with all these different geological processes, like trying to figure out what works.
Yeah. It's mind-blowing to think about all this activity happening like billions of years ago.
Yeah.
But there's still one thing I'm trying to wrap my head around.
Okay.
This plume-induced subduction initiation, or PISI.
PASI, yes.
It sounds like something out of like a sci-fi disaster movie.
It does, doesn't it? And the reality is just as dramatic.
Okay.
So this theory, it tries to explain how subduction zones, those places where tectonic plates collide and one slides under the other,
Yeah.
how those first formed.
Okay.
Imagine this giant plume of superheated rock rising up from Earth's deep interior.
Okay. Giant lava lamp is back.
Exactly. This plume rises and smashes into the Earth's crust with incredible force, cracking it like an eggshell.
Oh, wow.
And guess what? These cracks, caused by the plumes, they become the perfect breeding ground for subduction zones.
Wait, so you're saying that these massive plumes essentially created the fault lines where continents would eventually collide?
That's the idea. But we're talking about a time before the massive continents that we know today. Back then, you had smaller land masses called protocontinents.
Okay.
And they were constantly bumping into each other, breaking apart, and reforming.
So these protocontinents were like the building blocks, and PII provided the blueprint for how they'd eventually come together to form the continents we know today.
You got it.
Wow.
Now let's connect this back to the Olondo greenstone belt.
Okay.
The researchers believe that this unique combination of the dunites, the cometic basalts, and the thallatic basalts found there, along with that evidence for subduction, might be some of the earliest support for this dramatic PISI theory. It's just a glimpse into the powerful forces that shaped our planet billions of years ago.
It's like we've been piecing together a puzzle this whole time, and the Olondo greenstone belt just provided some crucial missing pieces.
Yes.
But I have to ask, and I bet our listeners wondering the same thing, why does any of this ancient history matter to us today? It's easy to think about this stuff like it's ancient history.
Right.
Totally irrelevant to our lives. But this is about more than just rocks, right?
Oh, absolutely. Understanding early Earth, it isn't just about like satisfying our curiosity about the past. It's about understanding the foundation of our present and our future.
Okay, so how so?
Well, think about it. Plate tectonics are still actively shaping our planet today.
Oh, yeah.
They're behind earthquakes, volcanoes, mountain ranges.
Like Earth still has that wild streak billions of years later.
Exactly. And by studying how plate tectonics worked way back when, it helps us get a better grasp on these processes happening today. We can even try to predict how they might change in the future.
So like a geological crystal ball.
Yeah, in a way, yeah.
That's so cool.
It's not just about predicting the future, though. Understanding early Earth helps answer some of like humanity's biggest questions.
Like what?
Like, how did Earth even become habitable? What were the conditions that allowed life to emerge?
So we're searching for our planet's origin story.
Yeah.
And the Olondo greenstone belt is adding a whole new chapter.
I like that. That's a great way to put it. And it highlights why this research is so compelling. By digging deeper into Earth's history, literally we're getting closer to understanding those processes that made life possible.
This deep dive has been amazing. Giant plumes cracking the Earth's crust.
Yeah.
Protocontinents playing bumper cars. Who knew ancient geology could be so exciting?
And the best part, there's still so much more to find out. Remember how we talked about the dating methods used in the study?
Yeah, the fact that those dunites were over 3 billion years old.
Yeah, and that just might be the tip of the iceberg. We could find even older evidence out there. We're constantly making new discoveries about early Earth.
It's really humbling.
It is. To think that these ancient rocks hold secrets for billions of years, just waiting for us.
That is a great note to end on. To our listeners, wherever you are, take a moment and think about the ground beneath you. Those rocks hold the story of our planet, a story that's still being written. And who knows, maybe you'll be the one to uncover the next chapter. Until next time, happy exploring.